Let's take a look at a few more slope field examples. We've got dy dx equals x. We've got dy dx equals y. Those seem like they're fairly similar sorts of graphs. So let's start by sketching a slope field on each one, and then we'll sketch a solution curve that goes through the point 1, 1. And then we will actually solve for that particular solution analytically and check in our calculator. So when dy dx is equal to something in terms of x, then it doesn't matter what y is. For example, if x equals 0, then dy dx equals 0, whether y equals 0 or 1 or 2 or 3 or 4. So at x equals 0, we've got horizontal lines everywhere. We have them down here as well. I'll just draw them up top. When x equals 1, our slopes are 1. And when x equals 2, our slopes are 2. And etc. So we get pretty steep pretty quick. And the same thing happens going in the negative direction, except we have negative slopes. So you don't have to spend a ton of time making these slope fields particularly accurate. Definitely focus on those zeros. We want to make sure those zeros are perfectly horizontal, and positive versus negative is pretty important. And then relative steepness is the other thing you want to look at. We can see that we're getting steeper as we go from the y-axis to the left or to the right. So there is a slope field for dy dx equals x. If I try to draw a solution curve through the point 1, 1, the particular solution, well, we can see that we're going to kind of head off in this direction, but we better get steeper, right? We better get steeper and steeper and steeper as we go to the right. As we go to the left, we better level off because we're going towards the y-axis where we know it's going to be a horizontal tangent line. And then once we hit there, then our slope becomes negative, and we're going to curve around this way. So maybe something like this. Okay. We'll try the same thing with dy dx equals y. This time it doesn't matter what x is as long as we know what y is. So if y equals 0, pew, 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 then the slope equals 0. You got to do those sound effects. That part's important. Now if we bump up to y equals 1, then our slope is going to be 1. So we still have a collection of slopes that equal 1, just like we had a collection of slopes that equals 1 on the previous example. But this time, the collection of slopes that equal 1 exist on a horizontal line rather than on a vertical line. So that fundamentally changes the shape of these curves. Kind of interesting to think about. So we bump up to y equals 2, and we get even steeper. So this time, as we shoot away from, or we travel away from the x-axis, we're going to get steeper and steeper and steeper. So let's go ahead and draw a solution curve through the point 1, 1. Okay, so this is, again, we're going to go this way, but we better get steeper. And by the time we get up to here, we're already at a slope of 2, and then by the time we get up to here, we're already at a slope of 3, and then we just get steeper and steeper and steeper. Watch what happens as we go the other way, though. We don't have this kind of U-shaped turning around business. Instead, as we get closer to the x-axis, our slope gets closer and closer to 0. But we're continually having this positive slope, so it looks like we're just going to kind of level off. We never quite make it to that horizontal line. In fact, because we've got a collection of slopes that are all collinear, right? Imagine a solution curve starting at this point. The slope tells us to go perfectly horizontal. We're going to end up at this point. And the slope still tells us to go perfectly horizontal at this point. When we see a collection of slopes that form a line like that, that's going to be an asymptote on our graph. So y equals 0 is in fact going to be an asymptote for all the solution curves of this differential equation. What is that differential equation? Why, I'm glad you asked. Let's take a look at the analytic approach here. These are both solvable using separation of variables. For number 3, we'll start with dy dx equals x. We'll separate the variables by multiplying both sides by dx. We'll integrate. We'll get y equals 1/2 x squared plus c. That's the general solution. Now, if we try to find the particular solution, we know that our particular solution goes through 1, 1. So we'll let y equal 1, we'll let x equals 1, and we'll find that c equals 1/2. So the particular solution is y equals 1/2 x squared plus 1/2. All right, that looks reasonable. A parabola who's shifted up by 1/2 from the origin. Now, if we try to do the same kind of deal with the other differential equation, I'm afraid I'm going to run out of space. So let's try to slide all of this work over this way a bit. All right. So we'll start with dy dx equals y. Separating the variables this time, I'll multiply both sides by dx, but I also have to divide both sides by y. So when I integrate here, I don't use the inverse power rule. Over here I did because the exponent was 1. Here the exponent is -1. So when I anti-differentiate that, I'm going to use the natural log. And over here I'm going to take my x plus c. So if I'm going to try to solve for y, I'm going to exponentiate and get y is equal to e raised to the x plus c. Okay? One thing we can do with these exponential functions is we can realize that because we've got an addition in the exponent, we can say that's e to the x times e to the c, right? Multiplying like bases means adding exponents, so I'm using that familiar property of exponents in reverse. But remember what this is. This is a constant raised to a constant, so that's just some other constant. So I'm going to write this as y equals c, some big constant c, times e raised to the x. Okay, and that's going to be a fairly common thing to do. Now, that's the general solution. The particular solution, notice that changing the c value doesn't do a vertical shift, right? But if we know that this curve goes through the point 1, 1, then we know that 1 equals c times e raised to the 1. In other words, 1 over e is equal to c. So we have the particular solution of y equals 1 over e times e raised to the x. Okay, and that looks like possibly the right sort of graph for that. If we tried to solve for c in this case, we'd probably get a c value of -1, and that might make sense because 1 over e is the same thing as e raised to the -1. So maybe we'll think about this as e raised to the x minus 1. They're both correct. All right, so if we wanted to check these, we would go to a calculator, and for this one I think I'm going to use Desmos. Desmos is a nice, has a nice slope field generator. Someone created it. I Google it, I find Desmos slope field, and this always comes up, and it's great, so thank you whoever made this. And here is the differential equation dy dx equals x, which looks an awful lot like the graph that I originally started with. The solution curve, it goes through the point 1, 1. There's the point 1, 1. We found that to be the parabola y equals 1/2 x squared plus 1/2. Boom. Not only does it go through the right point, but look at those slopes on the slope field. Look at how they're all pointing in the same direction as the curve, or rather, look at how the curve follows the direction that the slopes are going in the general area. Okay, so that seems to support that first answer. The second answer, dy dx equals y. I only graphed the positive slopes. We have the mirror image down here below the x-axis. And our point 1, 1 is right there. And then when we graph our particular solution, we notice that yes, it does go through the point 1, 1, and also it follows that slope field perfectly. So we feel pretty good about this these solutions here. So that would be a good way of A, solving a differential equation graphically, and B, checking that differential equation analytically. Now, this next example, we can't actually solve that analytically. Some people can, but we can't because we don't have the ability to separate x plus y. Notice that this is not x times y, this is x plus y, and that means all bets are off as far as separating. But we can still use slope fields. So, for example, when x and y are both equal to 0, our slope is 0. If x equals 1 and y equals 0, we've got a slope of 1, and then we get steeper and steeper and steeper as we go to the right. Or if we go to the left, we're going to get steeper and steeper and steeper in the negative direction. And then we'll shift up to y equals 1 maybe. So if y equals 1 but x equals 0, we get a slope of 1, and it's going to get steeper and steeper. If we go this way, x equals -1 and y equals +1, you add those together, you get 0. And you get that same pattern that we just got before, just kind of shifted over 1. So if we go up to here, this is going to have a slope of 2, because 0 plus 2 is 2. And then we'll have a slope of 1, and then we'll have a slope of 0, and we'll have a slope of -1, and we'll have a slope of -2. And you can kind of see where this is going, perhaps, maybe not. But this slope of -1 follows a line right here, right? 0, -1 adds to 0 plus -1 adds to -1. 1 plus -2 adds to -1. All of these slope lines are collinear. So it looks like we've got ourselves not a horizontal, but a diagonal asymptote here. And we've got a horizontal tangent line anywhere where x equals -y. And we've got a slope of 1 anytime x is 1 bigger than -y. Yeah, so we kind of have some shapes like this. Just to kind of get a quick graph here. 1, 1 is right here. As we go off to the right, it's going to get steeper. As we go off to the left, it's going to get towards those horizontal ones, and then we're going to start curving towards that asymptote, something along those lines. So that would be something of the solution curve through 1, 1. 0, -1, on the other hand, is going to start on this asymptote, and it's going to stay on this asymptote. So this is going to be a linear solution to this differential equation. And then lastly, we'll have -2, 0, that's right here. That one is going to, it's a little hard to see because I didn't graph a whole lot of this because of how much time I have. But it's going to end up looking like this. Now, we can't graph solution curves like this in the Desmos grapher. It can't solve differential equations, so that's when we're going to turn to the TI Inspire. If we graph, menu, analyze graph, graph entry, edit differential equations, we'll do x plus y1 and get my solution curve there. If I give it the initial point, what was it, 1, 1? Yeah, the initial point 1, 1, we can see that first curve that we created. If I give it that initial condition 0, -1, and the other initial condition, which was -2, 0, we can see those other two solution curves as well. And that kind of looks like what we graphed by hand. So that's a fairly convincing, I think, check in a calculator. We don't know what the equations of those curves are because we can't solve these analytically. At least not in this class, we can't. But we can definitely do some sketches by hand, and we can definitely use technology to check our sketches.